Hello everyone. So welcome to today's lecture. Today we will be continuing our discussion on the basic setup and some fundamental understanding of machine learning problem. So in today's agenda, we will be looking at an important discussion. At least I find that whatever we are going to discuss today very interesting. So in general, we will be tackling the question of why it works. By it, we mean machine learning, how it works. And so, in a way, we will be discussing a very small part of the success story of machine learning. Okay, so that is what we'll be doing today to help you understand why it work, what is it uh, that makes it function. And today's lecture or this lecture's discussion will lead nicely into the discussion on the VC dimension and on the other stuff. Okay. So in the previous lectures, we have discussed the formal setup of a machine learning problem, and the agenda for today's lecture is to get you started on understanding why it works and all those things. So for that, we will be limiting our discussion to only classification, the classification problem, because this has been well understood in the literature. So we'll be only discussing the classification problem. And just to recap our framework and the notations that we have had. So I am again and again talking about the formal setup and the framework and all those things just to make you comfortable with the notations and the ideas, because sometimes it is easy to get lost in a lot of things that has been said. So the pace of the lectures has slowed down, and it has been done deliberately for the sake of understanding. So what we have in the framework, first thing is our data. So we have, let's say, n data points, xi, yi. Xi is in the input space, yi is in the output space, and we have n data points. So these data points are sampled in an IID fashion from an unknown probability distribution. Unknown probability distribution on script x plus minus 1. Okay. So here, since we are considering the classification problem, that is why we have this. So two important aspects of a machine learning problem. First is that the probability distribution is unknown to us, and second is the assumption that the data is IID. Now, our goal is to learn a deterministic function that takes inputs from the input space and gives the output plus minus 1, and we have to do that from amongst a class of function f. Script f. Okay. And a, b, and the item c will be such that the expected loss according to some loss function L is minimized. Okay, so we are interested in minimizing the expected loss function. So there are three aspects to our goal, and this with these three aspects, this is the standard machine learning problem. So L here, since we're considering classification, the classification problem, L will be intuitively, I mean, the natural loss function is the 0, 1 loss functions. Okay. So we had discussed a few more details about this as well, and some notations and jargons that we will again use today. First is that of true risk, is that is, so this is the true risk is what we want to minimize. Okay. F is our function that we have learned. Y is the output corresponding to the input X. Okay, so actually we want to minimize true risk, and our target function, if we might call it that, or the optimal, is given by infimum input space to output space such that F is measurable, and other some other notations that we had is that the base classifier is the function that minimizes the risk. So the best function that we can achieve is the base classifier that will be denoted by F star. Then the another thing to note is that the best in the function class script f, it is denoted by f in script f argmin. Out of all those functions that belong to the functions class script f, the function that minimizes the true risk is denoted by f script f. Okay, so these were some definitions that we had, and based on this we also discussed the estimation error and approximation error, so we'll not recap that now. Now what we have is, let us say, an algorithm A which takes in the data endpoints, and it gives out a function fn. Okay, so fn is the function that is learned by the algorithm A from these data points. So of course fn depends on the sample that has been given to it. So now that we have defined fn, we can have a few more definitions. So first we say that algorithm A is consistent with respect to the function class and the probability distribution. So this P denotes the probability distribution with which the data has been sampled. If for all epsilon greater than 0, we have the probability that the true risk of the learned function minus all right. So this basically means that if the true risk of the function that has been learned by the algorithm converges to the best function in the class, to converges to the true risk of the best function in the class, then we say that the algorithm is consistent with respect to the function class and the probability distribution with respect to which the data is being sampled. Okay. Then the second, so here we have this difference is what is known as the estimation error. Okay, so the yes, so this is the estimation error. Now the algorithm A is called Bayes consistent. So we discussed these things in the previous lecture as well, but this is just to remind you and to so that these definitions and the concepts they become ingrained. The probability that the function that is learned converges in terms of its risk to the true function or to the then it is known as Bayes consistent with respect to p. Okay, so this here is the so this is like the total error. So this is not exactly the approximation error. Approximation error is something else. Now the third aspect is that which we will not touch upon. I mean, yeah, but it is just a semantic issue. Is that we will add universal to these two definitions, like universally consistent with respect to the function class f, or universally Bayes consistent if they work for all probability distributions. Okay. So here the definition it is contained. It depends on the probability distribution p that we are considering, but we will add just in terms of the jargon. We will add universally to the definitions if they work for all p. Okay. So an algorithm A is called universally consistent with respect to function class f if for all epsilon greater than 0 this works. For all epsilon greater than 0 and for all p this is true. Similarly, an algorithm is universally Bayes consistent if for all epsilon greater than 0 and for all p this condition is true. Okay, so this is just one of these semantical issues. Then the next thing which we discussed was that we said that since p is not known, we said that p is not known, we can't compute the true risk. So then we said that okay, so let us approximate the true risk. Just for the sake of completion, we'll just write both definitions here. So true risk is expected value R of f is expected value of the loss and the empirical risk is the approximation of the expectation using like how we calculate averages. Okay, so we have essentially uh, approximated the expectation using the average over the n samples, average loss over the n samples. Okay, and then what we do is that, and what we say is that algorithm A works with the empirical risk, and we say that the function fn learned by the algorithm is actually argmin, the function that minimizes the empirical risk. Okay, so the n data points, upon seeing the n data points, the algorithm it minimizes the empirical risk and finds a function. I mean, the algorithm tries to find a function f in the class script f such that the empirical risk is minimized. Okay. So in the rest of the lecture, we will be focusing mainly on the estimation error, on some back-end working of on some understanding of if we can find the best in class function. So when we say best in class, we mean f script f. Okay. So this is like the best in class. So given a function, a class of functions, script f, can we, is there any chance that if we have infinite amount of data that we will converge to the best in class? So this is what we will be discussing today. So we will be focusing on the estimation error. So this will be the prime focus of the now the first step in that analysis is to acknowledge that empirical risk is an approximation of the true risk. Okay, so that is the first step, that empirical risk approximates true risk. Okay. So now if we want to, and because our algorithm works with empirical risk, if we want to make any statements regarding the consistency of our algorithm, the first step is to see how well the empirical risk approximates the true risk. This is equivalent to saying that the sampled mean and true mean, if you remember from law of large numbers and from basic probability, that there are lots of results in, especially basically law of large numbers, that relate sampled mean to true mean. We face sort of a similar question here, where we have to compare the empirical risk with true risk. Okay. And the question that we are interested in is that, does empirical risk work? Why does it work? And when does it work? So these are vaguely the questions that we want to answer regarding to empirical risk. Now we know from law of large numbers that one the sample mean of a random variable zi, it converges to the true mean almost surely. Where here we have zi, they are IIDs. Okay. So if we have almost surely, then it is strong law of large numbers, and if we say it converges in probability, then it is the weak law of large numbers. So if you are not familiar with these terms, it is okay. Don't worry about these things. Just we can loosely call it that it converges to the true mean. Okay. And we also have another result which we have extensively devoted time to in our course on Chernoff like bounds, okay, which basically tells tell us things about the rate of convergence. So here we know that the sample mean they converge to the true means. Now the Chernoff like bounds, they tell us about the rate of convergence. And and okay, so here epsilon is greater than or equal to 0. So these are the Chernoff like bounds. So it might make sense that we use the machinery that we have already developed in the course to tackle this problem, because here also fundamentally what we want to do, what we want to analyze is the convergence of, or how well the empirical mean approximates the, or how well the empirical risk approximates the true risk. Okay, so law of large numbers and Chernoff like bounds, they sort of seem like a good starting point. So we will just use them and we'll make an observation that for a function f naught, in the function class f, we have Rn f naught. Okay. Because I mean, you can think about this. We can prove it using the Chernoff bounds as well, because empirical risk is just sum of the loss function, and the true risk is the expected value. So the Chernoff like bound, they are exactly the same. So we will have something like Rn of f minus R of f and so on. So you can, I mean, so it can be proved. So we'll not spend time on this. But what I really want you to spend time on is uh, on thinking that, are we done? Are we done with answering? Okay. So we started with the question that how well the empirical risk approximates the true risk. And we noted that we have the law of large numbers, we have the Chernoff like bounds, and using those two those tools, we can prove that the empirical risk of a function f naught, it converges to the true risk of the function f naught almost surely. Okay, so this can be proved. You don't worry. I mean, if you see the proof, then it is good. If you do not see the proof, you can try it out, and it is okay. But what I really want you to spend time on is thinking that, does this observation prove what we wanted to prove, that if empirical risk approximates the true risk within our framework? So this is one of the reasons why I laid out the framework again today. You can take 5 minutes, 10 minutes, 15 minutes, or half an hour to convince yourself. If we, whatever be your answer, just be convinced that whether this statement proves what we want to prove. Okay, so spend some time on it. So I'll just be telling the answer. If you got the answer right, then good. If not, then you need to spend some more time on understanding the framework and what is actually happening. Okay. So the answer is that the answer to this question is no. No, we are not done with proving this, because this observation works only for a fixed function f naught. So basically, and if you look at it from the law of large numbers point of view as well, we need the IID conditions. Okay, but what is happening with our algorithm is that there is that with every data point. Okay, so with every data point, even the function is changing. Okay, so the risk is also dependent on the number of data points, and the argument which we have for that risk, that also changes with respect to the data point. So put it a bit more formally, so what we are actually looking for is this quantity. Okay, tends to 0 as n tends to infinity. So in this quantity, as n increases, the argument of the risk, it changes. So Fn is not fixed. So if we have a fixed function, and if we take several samples of from that fixed function, then the law of large numbers and Chernoff like bounds, we can use that to do what we set out to do. But the problem here is that we do not have a fixed function. Okay, so as n tends to infinity, at every time step our function is also changing, because our algorithm is minimizing the empirical risk. As we already mentioned here, that with every data point, our algorithm here and later as well, that our algorithm minimizes the empirical risk and it gives a function fn. So as n increases, the function fn will change. Okay, it may not change as well in some cases, but if we have to consider a general case, then the function fn will change. Therefore, the law of large numbers, or the fundamental understanding of what we have about true mean and the sampled mean, does not directly applies to this case, because yeah. Okay, so that is the important changes at every step. Everywhere, by every step we mean as n increases. Okay, so so now let us discuss this more. So now what uh, so this is the expression of our interest. Okay, so this is the expression of our interest, and what we have is that our algorithm will be searching for functions inside the function class scriptf. And since the function is changing at every time step, we cannot directly apply law of large numbers and all those things. So one way to circumvent this problem is to stipulate uh, that it should work for all functions in scriptf. Okay, so we want empirical risk to be a good approximation. So this is our objective. So what we are saying is that since our algorithm will be searching in the space of the class, what we actually want is that for all functions in the class, the empirical mean should converge to the true mean as n tends to infinity. Yeah. So we'll abuse some notation. We'll not write n tends to infinity. We can maybe write okay. So uh, because we do not know which function the algorithm will end up giving as an output, we do sort of a worst case analysis, and we say that okay, so for all functions in our function class, the empirical risk should converge to the true risk. Okay, so our function, the function given by the output fn, will be one of these f in f. Okay, so if we say that it should work for all functions in this function class, then of course it will work for fn as well. Okay, so this is one thing, and to make the argument more pretty, we just, I mean, so we strictly write it as a worst case analysis. So what we want is the following: with high probability. Okay, so for if we have a data sample of size n, then we want the condition that the worst case function in our function class, for even that, the difference between the risk of the difference between the true risk and the empirical risk is less than epsilon with high probability. Okay, so what we are saying in words is that Rn of f approximates the true risk with high probability. Okay, we can also say closely approximates. So the true risk, the empirical risk closely approximates the true risk with high probability. Okay. So this is the whole idea behind this, and this idea gives us the definition of uniform convergence. For all epsilon greater than 0, limit and tends to infinity, probability that the supremum of functions in the function class script f, the difference between empirical risk and true risk greater than epsilon is 0. Okay, so this is the definition of uniform convergence. So the convergence happens uniformly on all functions in the function class. Okay, so this is the definition of uniform convergence, and I think you should have gotten an intuition of how all these things came about. Now we have a proposition which addresses the utility of uniform convergence. It says that if we have uniform convergence, then we will have consistency. Okay, so we are saying consistency with respect. So this becomes like a sufficient condition, universal consistency actually, with respect to f. Since we are talking about estimation error, so we will only be talking about this. Now to prove this proposition, we will prove. The proof is quite elementary. I mean, it just uses the definitions. What we will be proving is so this is the definition of consistency, that the function should converge to the true function. Now we will prove that this is less than or equal to probability, I mean the condition of uniform convergence. Okay, so this is, and the proof comes by using the definitions itself. So if we consider the argument of the probability in the left hand side, so by definition, risk of f subscript f is the smallest in the whole class. Okay, and fn belongs to script f, and f script and f has the smallest risk by definition. So this can just be written as rfn minus rf script f. I mean, so the left hand side will always be greater than 0. So we can drop the absolute value. Now we do some addition subtraction because we want to introduce the empirical error here. The right hand side has an empirical error term and the left hand side does not have any. So we will bring in the empirical error term. Okay, so here what we have done is added and subtracted the empirical errors of fn and added and subtracted the empirical errors for f subscript f. Okay, so this is what we have done, and for that we we then consider the following function: the behavior of this term. Okay, Rn Fn minus Rn F script F is less than 0. So this is the claim, and the claim is true by the definition of Rn Fn. Okay, because for these n samples, for the n samples that the algorithm has received, Fn is the best approximation. Okay, it might happen that if we receive more samples, then uh, if it might happen that our Fn plus 1 is different than Fn, but for these n samples, Fn is the best approximation, and this comes through by the definition which we have here. Okay, that Fn is the best function with respect to empirical error. Okay, so here we are evaluating the empirical error. So when we consider the empirical error, Fn is the best function in this class of functions. So for these n samples, so this is only true for the n samples that we have considered, we will have this relation. Now when we have this relation, since this is less than 0, we can drop this quantity to get an inequality. So this is what we will have. So we have two terms here. This is the difference between the true error and the empirical error for Fn. And the second term is the difference between true error and empirical error of FF. Okay, so this can be bounded by taking the worst case analysis. So we do the supremum, and we have so this, and by this observation we have an epsilon by 2 here on the right hand side. Okay, so therefore if we have uniform convergence, then the algorithm, or the algorithm which uses empirical risk minimization as is consistent with respect to F. So uniform convergence is a sufficient condition, but in fact a remarkable result is that it is a necessary condition as well. So this was proved 50 years ago by Vapnik and Chervonenkis, and the theorem basically says that if F, let F be any function class, then empirical risk minimization principle, then for empirical risk minimization principle to be consistent with respect to F. Okay, but here since we are using universal, we will just say universally consistent. Universally consistent with respect to F, then empirical risk minimization principle is universally consistent with respect to F if and only if uniform convergence holds. Okay, so I mean what it means is that supremum F in script F this is a very deep result in the sense that it says that the necessary and sufficient condition for us to find the best function in class is that the true risk should be equal to the empirical risk for all functions in f. Okay, so that it should be true for everything, all the functions in f. We will not be discussing the proof that it is necessary. We have looked at half the proof that of the sufficient condition. We will not look at the proof for why it is a necessary condition or not. So in the next part of the lecture, we will rather be addressing that if we have been given with a function class f, how do we know whether we have uniform convergence? Okay. So given a function class f, how do we test if we have uniform convergence or not? So this is an important question that we want to address, because we have a necessary and sufficient condition, but that necessary and sufficient condition is not of any use if we cannot test it. Okay. So next we will be discussing it, and for today we will only focus on finite classes. Finite function class which has finite number of functions in it. So suppose it has m functions. Let us say f has m functions in it. Then we can just use union bound. So what we have is that supremum, since we have m functions in the function class, we have to find the supremum over these m functions. And we need this condition to be true. Now the probability that the supremum is greater than or equal to epsilon, uh, yeah, so we can approximate it by saying probability that the first function is greater than or equal to epsilon, or the second function is greater than or equal to epsilon, or, and we'll do it till m functions. Okay. Now we can use the union bound. No, because we have a constant, the same function inside the argument, we can use the Chernoff-like bounds to get this equation. Okay, so for a finite function class, we can check if, so what it basically means is that given an epsilon that lies between 0 and 1, we are saying that the empirical risk is epsilon close to the true risk with probability 1 minus 2m e raised to the power minus 2n epsilon square. Okay, because the right hand side was greater than or equal to epsilon, but what we want is the true risk and empirical risk to be less than or equal to epsilon. So what these steps have told us is that the empirical risk approximates the true risk for any function in f with probability 1 minus 2m e raised to the power minus 2 epsilon square. Okay, but the way this inequality works is that we first propose an epsilon, then given that epsilon, we get the probability. Okay, so in some applications, this is an interesting question, that if we can tolerate an error of certain amount, then yeah. So given an epsilon, we then get the probability. But in some time, but we are interested here in saying that we want to be 95% sure. Then what is the error for us to be 95% sure? So what we want is, given a confidence level, what is the error? Okay. So yeah, so we are saying that I want to be 95% sure what is the value of error. What is the value of error corresponding to a given confidence interval? Okay, so given confidence. So what we are asking for, I mean that can be easily found by equating delta to this quantity, and what we have is that epsilon is log 2m plus log 1 over delta divided by n. Okay, so uh, this is also called the generalization bound, and that bound is okay. So here first, given a delta, so we pick the value of delta, and then we get the bound that we want to have on this. So I like to make a couple of comments on the bound. So what it is actually saying is that on the left hand side we have a true risk, and then on the right hand side we have empirical risk plus a capacity term. So we are using the capacity term here as an indicator of what is to come in the next lecture on Vapnik-Charbonenko's dimension, VC dimension. So this term here is the risk term, and M is the number of functions in the class. Okay, so M is the number of functions in the class. That is why we are calling this whole term as a sort of a capacity term. If we have infinite amount of data, as n tends to infinity, the whole expression inside the square root, it tends to 0. So our yeah, and so this some sanity check. And then the other observation which is interesting is that if log m divided by n is small, we get a tight bound. Okay, because this term it goes to 0. So these are the two observations on this. So what we have seen in general in today's lecture is that what role does empirical risk has to play in the consistency of our learning algorithms, and we majorly defined, or the main concept that needs to be grasped from today's lecture is that of uniform convergence, that we want all the functions in our function class to converge uniformly, in the sense that their empirical mean should tend towards the true mean. So this is like a worst case analysis. We only saw the finite function classes, and we the proof here, it worked out because we have a finite number of functions. But at this point it is not really clear what will happen if the function is infinite, so function class is infinite. So this is something which we will discuss in the next lecture, and this will lead into the discussion to VC dimension. Okay. Yeah, so that's all for today.